All right, so implicit differentiation. What that means is, like we just said, is we're going to be taking the derivative of something that is not a function. It is not just y equals. You're going to maybe have multiple y's in there, and maybe you can't even solve it for y. Some of the easy ones we start off with, you will be able to solve them for y. So we'll show you how it works either way. Okay? So we want to look at these. Now, if we had the first one, could we take the derivative of that, dy dx? Yes, you'd have to use quotient rule, down d up, minus up d down, all over, down, down. And then to deal with e to the x squared, you would have to use chain rule, but we could do that. When we take this function and we want to find the derivative of that. Now, think back to this again. Remember, this is, when we first started talking about derivatives, it was the slope of the tangent line. That's what it was, right? It's still going to be the same here, slope of the tangent line. The difference is that's the graph. So it doesn't pass the vertical line test. So what that means is if we have an x coordinate right here, we want the slope of the tangent line. Before, everything we've looked at is functions. So your derivative had an x in it. Now, you're going to get a different answer here. You're going to get a different answer here, and you're going to get a different answer there for what the slope of the tangent is. So when we end up with our dy dx, whatever we end up with is going to have x's and y's in it. We'll have y's in our answer because when we go to find what's the slope of the tangent line, we need both what the x coordinate and the y coordinate is at that point to find the tangent line because you have both x's and y's in that point. Okay? All right, so let's kind of build up to this here for a second. So from what we've already done, if I say what's the derivative of x squared? That is just 2x. Do we have to multiply by an inside part with chain rule? There's really no inside part, right? So let's say we have sine squared. What's the inside part? Is the sine. So our derivative would be 2 times sine, right? We subtract 1, times the derivative of the inside, which is cosine. Let's say I have 3x squared minus a squared. That would be, you'd bring down the 2, 3x squared minus a, you'd subtract 1, times the derivative of the inside. Right? Our whole chain rule. Derivative of the outside, inside staying the same, times derivative of the inside. So we're still using all those rules, right? So we're still going to have product rule, quotient rule, and chain rule. Those aren't going away. But we're just going to continue to use them. So if we have something like this, the derivative of y squared, where y is some function of x. We don't know what it is. Let's say this is y. Or let's say the sine is y. Notice what we do in both of these. We bring down the 2. The y, whatever it is, stays the same, right? Times dy dx. So if we're taking the derivative and this y is the inside part, we take the derivative of the outside, inside stays the same, so it stays y, times the derivative of the inside, which should be that. Okay. So these follows the same pattern. So let's say another one. what would be the derivative of cosine of y? Remember, y is some function of x, but we don't know what it is. That's what the implicit is. So what's the derivative of cosine? Negative sine. Times the derivative of the inside, which is dy dx. Now, here's the key. One, you can really remember this and try to understand why. Or anytime you take the derivative of y, just throw out a dy dx. That's basically what's going to happen. And that will get you there. Okay? So let's look at some examples to see how this works. So let's say we have y squared equals x. And we want to find dy dx. Okay? So y squared equals x is this parabola on its side. So what we're going to do is we're going to take the derivative of both sides. So take the derivative of both sides. Well, the derivative of x is just 1. And the derivative of y squared, we just talked about that, is 2y times dy dx. So you're trying to find dy dx. So once we do that, we want to solve for dy dx. So we divide by 2y, and there is our derivative. So dy dx is equal to 1 over 2y. So you'll notice this one does not even have an x in it. So if you wanted to try to find the derivative somewhere, right? If I wanted to say, well, what's the derivative right there? Well, if x is 2, what is y? Y would be the square root of 2. So then I could put that into here to get what the derivative is. Okay. Now, we could do this another way. So let me try to show you here how this is. We could do this another way. Imagine for a second I took, remember we have y squared is x, and I solved that for y. So I could write y squared is x as just the square root of x. And if we go back, this would just be the square root of x, right? And then this would be negative square root of x on the bottom. So let's say, what would dy dx be here? Well, how do I take the derivative of x to the 1/2? I bring down the 1/2. I subtract 1. That's 1 over 2 square root of x. Now, I'm just trying to show you what's going on here. Square root of x is equal to y, which gives me that. So you can kind of see I got the same thing two different ways. This works when I can solve it for y. Usually you can't solve it for y. That's unusual that you can solve it for y. Okay. And if we did this one over here, we would get similar idea. This would be negative 1 over 2 square root of x. But then the original y was negative, so this is still the same thing. Okay. We're not going to do that a whole bunch. I'm just trying to show you it works either way. You get the same thing. All right. Let's look at this one. X squared plus y squared is 4. And we want to find what is dy dx. Okay. So we need to take our derivative. So here's how, this is the key. So if we take the derivative, what's the derivative of 2x, or excuse me, of x squared? 2x. But it's x, so we're good. Plus we take the derivative of y squared, which is 2y times dy dx. Then we equals the derivative of 4 is 0. That's the step people always forget. They always have that equals 4 over there. They just write down 4 again. Remember, the derivative of a constant is 0. Now we need to solve for dy dx. We're going to subtract negative 2x to the other side. Divide by 2y. And we get the derivative, we get dy dx is negative x over y. So when we're doing explicit differentiation, our answers can have both x and y in them. And like I said, one key to think about this is just every time you take the derivative of the y, it just kicks out a dy dx. That's what's really happening when we do this. Okay. Now, if we wanted to find the derivative at a point, we can now find dy dx at that point. I'll introduce this here for the first time. That's that vertical line, 1 square root of 3 is just a mathematical way of writing, I'm going to plug these two numbers into the derivative when we don't have functions. So 1 square root of 3, so this would be negative 1 over the square root of 3. Now, if you remember this, x squared plus 4, if you remember, that's a circle of radius 2. So we were 1 square root of 3, which should be about right there. And so the slope of our tangent line looks to be negative. And what did we get as our answer? Negative 1 over square root of 3, right? So it worked out. You can see that it works out to be what we think. Makes sense, holds up for what we're doing. All right. Let's look at another one. So there is a graph of that, but let's say we want to find what is dy dx. So first off, how would you take the derivative of the product of x and y? You have to use product rule. What your product rule is? Derivative of the first times the second plus the first times derivative of the second. So what's the derivative of y? It's 1 then times dy dx. Plus the derivative of 2x is just 2, plus the derivative of 3x squared is 6x equals 0. Now we are solving for dy dx. So if we're solving for dy dx, we take everything to the other side. And finally, we divide by x. I'm going to make this. I'm going to put the negative on the bottom instead of all the ones on the top being negative because I just think it looks nicer. So the key here is you take the derivative of each piece, then you solve for dy dx. Okay? Let's try two of these. Try that one. We won't worry about the slope of the tangent line. Just see if you can take what is the derivative of that using explicit differentiation. Implicit. So the derivative of y squared is 2y times dy dx minus 8x equals 0. So dy dx, we take the 8x to the other side, we divide by 2y, the 2's cancel, and we get to there. Which you can see, once again, if we look at the point over here, if we were at a point, let's say here, 2, if we looked at those 2 points and we looked at the slope of the tangent line, it looks like they would be the exact same number, except down here your y is negative, so you get a negative slope. Up here, your y is positive, so you get a positive slope. But they can't be the same number. If one was 2, the other would be negative 2, or vice versa, right? So that kind of makes sense with what our formula. All right, another one. Try that one. A little harder. All right, so derivative of x cubed, 3x squared. Derivative of y cubed, 3y squared, times dy dx. So for the negative 9xy, we have to use product rule. So I am going to treat the negative 9xy as my first term. Okay? So this is my first, this is my second. So I will say plus the derivative of the first term, negative 9 times y, plus the first term times derivative of the second, which is dy dx. Now, we are solving for dy dx. So we have two terms with dy dx. I'm going to keep them on the same side. And I'm going to move everything else, negative 9y is just 9y, 3x is negative 3x, to the other side. Now, the big step here, anytime we do these kind of problems, is always this step. This is the step that people always struggle with, is I'm going to factor out the dy dx. And then finally, I can divide by that. To get to there. If I wanted to, I could just leave it at that. If I wanted to divide a 3, I could take out a 3 out of every single term. To get to there. Now, implicit differentiation can get a lot more difficult, and we're going to do more with this as we go on. We want to introduce it here today because there's two things we still don't know how to take the derivative of. We know how to take the derivative of a lot of stuff. One of the things we don't know how to take the derivative of is a logarithm. How do you take the derivative of natural log? At this point, we don't know. To do that, we have to use implicit differentiation. So that's what we're going to get into to just learn our derivatives of logs and some things. And then we'll kind of get into more of this and talk more about this and practice with this. So at this point, we're just trying to get all of these kind of rules down, and then we can spend some time just trying to like learn them better and understand them better and all that kind of stuff before we go. This chapter 3, is huge. Like, we may finish this chapter by Christmas. I mean, that's how big it is. It's got like 12 sections. So we'll probably at some point here, like stop, have a test over the first half, and then get into the second half just because it's so big. That's far away still. But so it's just, this is a lot of rules we're trying to learn right now. So before we can figure out like what can we use this for, we just want to try to help us to learn all these, okay? All right. As I said, I won't be here tomorrow. Homework is over Delta Math. Let me get that up here. I'll show you kind of what it is.